Hi everyone, welcome to the Earth Science Regions Review podcast series created by Hommocks Middle School Earth Science Department. Today we're going to talk about the Earth's oceans. Now the Earth's oceans are such a vast feature here on the planet, they actually cover about 75% of it. So 75% of our Earth is covered by salt or saline water. Most of the change within the oceans can be found right along the shoreline, and we'll get into a little bit of that change a little bit later on. Let's start out with actually the topography that's underwater. You have a good portion of the continent underwater called the continental shelf. That will give way to the continental slope, which is kind of the end of the continent underwater, which gives rise to the abyssal plain, which is the beginning of the deep water section of our oceans. Now on the abyssal plain, you have some features. You have trenches, you have ridges, you have islands, you have underwater mountains called seamounts, and you have underwater mountains that are flat tops called guyots. So you have a significant number of features that can be found along the ocean bottom. Notice that the ocean bottom is not completely flat. Now, there are a number of parts that you need to have an idea about regarding waves. And if you have any recollection about the electromagnetic spectrum, those same features will be applied to ocean waves as well. And that includes wavelength, the crest of the wave, the trough of the wave, and also the amplitude of the wave. So make sure you have an idea in terms of different characteristics of the waves themselves. Now, waves themselves are important because they're the main reason for the changing shoreline. And waves are going to be created by the circular pattern of the water molecules. The bigger the circular pattern, the bigger the wave is going to be. And essentially, that's going to be associated with wind speed. And we'll talk about the relationship between the two coming up. There's your circular pattern of your water molecules creating your waves. Now, there are a couple factors here that are going to determine wave height. And the first and number one reason is the greater the wind speed, the bigger the wave. There's a tremendous amount of friction between wind and water, and the more friction that there is, the more energy is going to be transferred from the moving air to the moving water, the bigger the wave is actually going to be. We also want to measure how long the wind has been blowing across the water and the distance it's been blown across. The distance is what we call the fetch. So you can see how big some of these waves actually can get. Now, waves are going to carry sediments. That's what we call longshore drift or longshore currents. Longshore currents are going to carry sediment to the beaches. They're going to travel parallel to the shoreline and deposit sediment on the beach itself, which will basically make the beach get bigger. So you can see how the longshore current is going to carry their sediment to the beach, and that sediment is going to be deposited on the beach. Now, there are some man-made structures that are going to be put out in the water to disrupt this longshore current. These structures are going to reduce the amount of erosion going on, but also stimulate deposition. And they're going to include jetties, groynes, and breakwaters. Let's take a look at them. Jetties can either be rock walls going out into the water to disrupt the longshore current, or they're going to be wooden walls as well. They're both going to stimulate deposition. Groynes are going to be slotted fences that are going to allow wind to pass through, but they're going to limit the carrying power and also reduce the amount of dune migration. And then finally, breakwaters. Breakwaters are big walls that are put out into the water to allow waves to crash into. They're going to lose their carrying power, which is going to basically lead to deposition on the beaches. So there's your breakwaters there. That leads us to basically the purpose of a jetty. Okay, your jetties, again, are going to basically be put out in the water to stimulate deposition. So one side of your jetty, you're going to get deposition. The other side of the jetty, you're going to get a little bit of erosion. Now, the side of the jetty that's going to get deposition, that's the side that's going to tell you where the waves are coming from. So if you're looking at a jetty and the left side is built up more than the right side, the waves coming in from the left. If the right side is going to be built up more than the left, then your right side is going to be the area in which the waves are coming in from. So when you take a look here, you see that the two jetties are put out into the water. You'll notice the longshore current is going from left to right across the picture here. So you see the word accretion, that also means deposition. So the left side of the jetty is being built up more, so the waves are coming in from the left. Here's an actual photograph. Notice the left side of the jetty is much, much bigger than the right side, so your waves must be coming in from the left. Now, you do have some depositional features that we need to kind of talk about. One is what we call a spit. That's going to be a narrow sandbar that almost acts like a finger, and it shows the wave direction. And also barrier islands, which are narrow bands of sand that can extend for hundreds of miles along a coastline that basically make a very, very narrow island chain called a barrier island. And a good example of this might be Long Beach Island in New Jersey. And these things are actually good enough and big enough to actually protect the shoreline. So when you take a look, here's spits and barrier islands. So here's a regions diagram that shows the spits. They act like a finger. They're telling you that the wave direction is from left to right across this picture. And here's an actual photograph of a spit, which is telling you the direction of motion. Here's a barrier island regions diagram off the coast of Texas. And here's an actual photograph off the coast of New Jersey. See the narrow strip there, usually need a little bit of a bridge to get to there, but essentially you're looking at a barrier island. Now, our ocean currents are extremely important here because, first off, they're going to be powered by our sun. They're going to help distribute energy across the planet. So ocean currents bring cold water towards the equator, and ocean currents bring warm water from the equator towards the poles. So there's a constant circulation of energy, there's a constant circulation of nutrients throughout the entire planet. So you'll notice here that your ocean currents are going to be a major conveyor belt with cold water sinking and warm water rising. Essentially, you're going to get a major convection cell throughout your oceans throughout the planet, just like convection in the asthenosphere, just like convection in the atmosphere. Your ocean currents work the exact same way. What also is going to have a major impact here is the deflection of your ocean currents. Your ocean currents are going to be affected by the Coriolis effect, just like your wind belts are, very simply because ocean currents are fluid. So you see here's the major convection belt all the way throughout the entire planet. The blue represents the cold water that's going to sink. You see the warm water is relatively red or orange here, which is going to rise. And also you can see here, very simply, if you look at the North Atlantic and the South Atlantic, and also if you look in the North and South Pacific, you will notice that the ocean currents are being affected by the Coriolis effect. You'll see that your ocean currents, for the most part, go in a clockwise direction in the north. They're deflected to the right. Southern hemisphere, they're in a counterclockwise direction, deflected to the south. So make sure you check out my podcast on page 4 in the reference table. We get into a little bit more detail about that. So that's it for now on ocean currents. We'll talk to you soon.